So some additional messaging that we want to kind of get across around Scribe is that Scribe is efficient block storage. And this has always been the case, but there's some new developments in hardware like NVMe that are now actually going to be able to demonstrate this quite well, I think. You know, when we started off with building Scribe about 5 years ago, we kind of looked at what was being done in the industry. We had a lot of experience with other clustered storage systems from the previous product, the SAN and the NAS appliances, and louder still. Right? So we took a lot of those lessons that we learned and wanted to build an efficient storage engine, and we made a lot of design decisions early on that basically give us this today. The fact that we have no file systems in the data path is a huge one. No storage protocols involved. There's no, sort of NFS connections between VMs occurring or any other potential bottlenecks via storage protocols. And there's no VM in the data path. There's no virtual storage appliance. We've taken Scribe and integrated it directly to the hypervisor, which really gives you a sort of a much simplified data path and gives you some performance advantages. And you know, with the advent of NVMe storage, this kind of stuff is really starting to pay off because as we're finding out, Scribe is able to actually reach performance near what you would expect from bare metal. And that's turning out to be quite a challenge for other storage stacks. I mean, I feel like they'll get there eventually, but there's a lot of significant software changes that have to happen for some of the newer hardware that's available now. So, a couple weeks ago, we announced this. We sent out a press release and launched with a white paper this product called HyperCore Direct. And what that is really kind of the next evolution of Scribe. And it is a version of Scribe that is basically been reworked a little bit to take best advantage of NVMe and really showcase the architecture there and the performance that's possible. So what is HyperCore Direct specifically? Again, it's similar to HC3. It is an HCI solution that fully utilizes NVMe and NVMe over fabrics. It's based on the HC3 software stack. It's technically just a branch of HC3 that we're working on right now. And it comes down to, we have taken Scribe, augmented it with NVMe support and NVMe over fabric support, and which means that it can consume storage via NVMe and NVMe over fabrics, whether that's local storage or some NVMe over fabrics array. That storage can be consumed as well. And then also shares the local storage on the hyperconverged node with other Scribe nodes via NVMe over fabrics. So we're taking full advantage of NVMe over fabrics wherever we can. And again, the background here with this project was really that we wanted to show the performance potential of Scribe. We wanted to, the fact that we knew that the architecture was fast enough and would take full advantage of the new hardware, we felt that this project was definitely warranted to kind of get a lead on these sort of opportunities where performance is really important. So the goals of the project are, again, we're migrating this technology into HC3 over time. It's not there yet, so you can't go buy a HyperCore Direct system in a standard SKU. It's not off-the-shelf system. What we're doing is engaging in custom deployments with a few select customers and partners, people who are interested in this and need it now. And in particular, we're getting a lot of interest from analytics and HPC customers who are sort of getting their feet wet right now with virtualization applications that typically have needed bare metal performance because the virtual machines and virtualized infrastructure cannot give the level of performance required. And HyperCore Direct is now able to do that. So we're starting to engage with those type of customers. And I think through this process, we're going to learn a lot about how best to configure the systems. And honestly, NVMe and NVMe over fabrics hardware is a little bit of a moving target right now as well, which is another reason why it's not yet available in standard SKUs. But we're expecting that sometime next year likely would be these sorts of technologies are going to be available in HC3, and we'll see what happens with the rest of the NVMe hardware and what's available for HC3.
Let's ask a question on that. So I don't know if I've misinterpreted what you're saying. So are there going to be HyperCore storage-only nodes for NVMe consumption?
There could be. I mean, it really comes down to, in custom deployments, we're willing to do those sorts of things, right? Depending on what the compute versus storage requirement is of any particular customer, we can certainly have storage-only nodes, compute-only nodes, or a combination of the two in sort of a converged node. But the nice thing about NVMe over fabrics, and I'll talk a little bit about that, it's so efficient that the storage is as if it's local. I mean, there's the latencies are extremely low even on remote storage. So storage-only nodes with NVMe over fabrics really start to make a lot of sense as well. If you need say a much larger amount of storage than compute, it might make sense to have a rack of have half the rack just dedicated to storage nodes, and then have several more hyperconverged nodes running just compute and storage. So,
although since I'm not buying VMware for the non-storage only nodes, the economics aren't going to be the same as for something like Nutanix, where it's $12,000 in VMware to add storage or a storage only node.
Right, and the storage only nodes can really be very, very simple. With NVMe over fabrics, there's a lot you can do with CPU offloading, or where you offload the processing of the target side into,
you end up having to buy CPUs because they have PCIe channels, not because they have cores.
Yeah, that's actually accurate. Yeah, so you start to need a lot more PCIe channels too, especially these boxes that have 48 NVMe drives in it. It's a crazy amount of PCIe channels. You need PCIe switches in there, and
AMD's EPYC should be attractive to you guys.
Yeah, I've started looking at that. It is very attractive. Okay, so with all this NVMe stuff, and there's a few pieces of new technology that had to go into Scribe to really make it as efficient as possible. I mean, these things aren't strictly required, but they really are kind of the key pieces that give us the extremely low latency that we're able to see. The first one here will be called vhost Scribe, which is a VirtIO backend. Now, what this is VirtIO, many of you are probably familiar with, is sort of the paravirtualized storage driver that's utilized by virtual machines, especially on HC3. With KVM-based virtual machines, you need a VirtIO driver in order to do storage. But traditionally, with VirtIO, you have an emulated device behind that in the hypervisor that could be implemented using a number of different storage protocols, or could be a local file on disk. But the point there is that you still have a hypervisor in the data path. You're still emulating a device on the back end. Well, vhost kind of serves to fix that problem. It gets that bottleneck out of the way. And where vhost kind of originated was in network packet processing. If you're potentially processing millions of packets per second in a VM, you need a highly optimized data path to do so. And when you think about NVMe and the levels of performance possible with NVMe, you need to start thinking of IOs differently. You're no longer scheduling an IO that can occur later once a physical armature has moved to a particular part of a platter. Like, those days are long gone. There's just a lot more volume of IO these days, and having this optimized data path with vhost and adapting vhost to use for block devices is really removes a huge bottleneck. The second major piece that we have is similar. It's an NVMe user space driver, which has a similar effect in that you've eliminated the kernel involvement in any I/O. So I actually got a diagram here that'll probably help explain these things. So this is kind of a diagram of what the data path looks like, and it's really simple. I mean, there's really not much. There's really nothing missing from this diagram, and that's kind of the point. Is that you have a VM with an application running in an OS. Below that, you have Scribe, and vhost, the piece I was just explaining, is what really lets the VM talk directly to Scribe without any hypervisor involvement. Right? The VM and Scribe actually have a shared memory data path, and when the VM needs to perform an I/O, there's no system call or context switch or anything necessary to communicate that to Scribe. Scribe's already watching those the VirtIO rings in there and can react immediately. And then similarly on the other side here, between Scribe and the NVMe devices and RDMA NICs for remote IOs, there's nothing standing in the way. With the user space NVMe driver, you don't have a kernel involved at all. You don't have to make a system call to perform an I/O. You're able to do that directly from within Scribe. So the data path is very, very simple. You don't see any file systems here. There's no VMs. It's just this.
What type of performance benefits do you get from moving it from the kernel to the user space
Well,
without all that overhead?
when your NVMe driver's in the kernel and you want to submit an I/O, what you have to do is you have to make some kind of a system call to the kernel to tell it, I want to perform an I/O, or here's my buffer where I want you to read or write to. And any system call involves basically a context switch into the kernel, which then causes TLB, cache misses, and et cetera. And all of these sorts of things are sources of latency. In many cases, you can think of the latency of a system call can be on the order of tens of microseconds in some cases. And when you're talking about storage devices that have latencies on the order of tens of microseconds, you have to really be careful about system calls that are in your data path. So by eliminating those altogether, you eliminate potentially a significant bottleneck. It's kind of interesting actually to run Scribe, this version of Scribe with and be able to attach to it with a tool called strace that shows system calls, and watching Scribe doing millions of IOPS and not making any system calls. It's kind of surreal. It's kind of a geek out point, but it's a pretty neat thing to see, having all that stuff in user space. So this is sort of an example of what the I/O data path might actually look like. You have an application in a VM that wants to perform an I/O. It's going to go through the OS there to do so. Not strictly speaking, but in most cases that will happen. You could have applications that also implement a user space driver, but in most cases it will go through an OS. There is a system call involved there internally, but beyond that, it goes right into Scribe. There's what we call a VSD layer, virtual storage device layer. This is where things like the reliability and snapshotting, et cetera, is implemented. This will actually perform the underlying IOs to the physical devices for you, in which case, with a reliable write, you need to write it in two different nodes. So you have one write that'll occur locally to an NVMe device, and the other write will occur via RDMA, via your RNICs, and then reach Scribe on the remote node, which will then issue it locally on the NVMe SSD there.
Phil,
Yeah.
how is your user space driver related to the SPDK DBT?
It is the SPDK user space driver.
Well, that makes that much sense.
Yeah.
Answers that question.
I was
Relates
expecting, and we
very-
tweaked it, but
Very closely. No, we're pretty much using the NVMe driver as is in SPDK, and that's SPDK is a great framework, and it's still pretty early on, but the NVMe driver itself has been working great for us, and that's really the only component of it that we're using.
yeah, but
So that's
it's shocking how much work Intel's done to accelerate the move to NVMe through that kind of thing.
yeah. No, when we started looking at SPDK, which is probably it feels like probably at least a year ago, maybe even longer. But yeah, it was shocking to see the performance difference between what you could do with SPDK and what you can do in the kernel, and it still is today. The SPDK, the user space driver, is just much faster, phenomenally faster. So, and then the nice thing here is that with Scribe using a standard NVMe over Fabrics protocol, this opens up the possibility to us taking advantage of hardware offloading of the target side processing. And this is it's still a little bit of a new feature on some of the NICs that let you do this, but the idea is what you will ultimately be able to do is run a remote I/O that will travel through the RNIC and then land directly on the drive without any CPU involvement. And then and NVMe itself being a moving target, the new standards are even adding things like controller memory buffers, which we'll also be able to take advantage of, where you have the memory buffer that is being written to prior to writing to the media. That memory is actually in the drive itself. And so that way you avoid consuming memory bandwidth on the remote node as well. So there's really a lot of neat optimizations that are still coming with the newer NVMe standards. So using the NVMe over Fabrics protocol as is with HyperCore Direct, we can fully take advantage of all those neat features as they become available. So I'm going to give you guys just a quick sample of some performance stuff and show you kind of the UI and show you it functioning. And this hardware that I'm going to show you is it's basically one of those 4-node 2U systems. So you've got like 4 sleds that go in there. It's an Intel board, the 2600 TPR. And each one of these nodes has 2 of Intel's P3700 2TB drives. And so 8 drives in the system total. Each node also has a Mellanox Connect X5 running at 100 gig. So overall, just pretty small footprint system, just a 4-node system. All right, so I'll switch over to that UI here. So this is it. And so today I've got 64 VMs set up on it and running various workloads. And you can see that this is the performance numbers we've come to expect from NVMe solutions are the millions of IOPS range with very low latency. And that's the numbers themselves aren't that surprising, right? You look at the specs on the drives. This is what you should expect from drives that say they can do 400,000 IOPS a piece. Sure, you should be able to get these numbers. But again, the challenge is having a software stack that can actually drive it that fast. And that's what we've tried to do here. And then on top of that, provide that level of performance to virtual machines. So you have a virtualized infrastructure now that is able to take advantage of these levels of performance. You can look
Bill?
Yeah.
The 317 microseconds of latency,
Yes.
where is that measured?
So that's measured in Scribe.
Okay, so that's to the VM, not to the application in the VM.
That's correct. That's correct. Yeah, and it's showing a latency gauge is tricky because you're absolutely right. We're not asking the application what latency is it getting. And so a lot of the benchmark testing that we've done, and you can see in the white paper, is using FIO inside of VMs. So the latency that it reports is actually what it's getting.
Right. And how much?
It comes pretty close to that. I think that it's still in the 300s, at least in this case. But again, yeah, it depends on the guest OS too and how
Right. Yeah.
efficient it is.
I mean, really, what you're measuring there is how smooth, how clean the guest
Yeah.
OS path is.
Yeah, and there are tricks to that because, like, especially with older OSs that weren't written with NVMe in mind, you might have higher latency because the OS is not expecting an I/O to come back in.
So is the para-virtualized driver in the OS still seeing SCSI, or is it a para-virtualized
No,
NVMe driver?
it is not seeing. It's just seeing. It's a VirtIO block, so it's not.
Okay, so it is
not
kind of
SCSI.
SCSI.
Yeah. So yeah, that's these are numbers that you'll expect. You'll see individual VMs doing over 100,000 IOPS a piece. With and really what that is in some cases you end up getting CPU limited in the guests. So.
Okay, and Scribe distributes data across the cluster without paying attention to locality to the VM, right?
Correct.
Okay.
Correct. Yeah.
Dear people who think locality is important, 350 microseconds too small, too bit much for you?
Yeah, and especially with NVMe over Fabrics, like the latency of the remote IOs is, it's almost non-existent. We're talking single-digit microseconds added latency for the remote side. The data could be anywhere, really. And this is kind of an example of a quote legacy OS that is seeing low latency. In this case here, it's a screenshot from a Windows 7 VM that was running on this cluster, and it's just single queue depth reads here are seeing 101 microsecond mean latency. And so what that means is you have legacy applications, and this is really kind of important. Like low latency is key here. You can see millions of IOPS and everything, and that's interesting, but it's really not that important with a lot of workloads. What is important though is latency, and that's what NVMe gives you. With 100 microsecond latencies, if you have a single queue depth job, this could be a database export or import, sort of real world workloads that end up being single threaded. and depend on a single I/O in flight at a time that maybe historically have taken, on the order of 1 to 10 milliseconds. When you cut that latency down to 100 microseconds, you're potentially going to be 10 times faster in some cases, right? So it really makes a big difference. It's
And the paradoxical part is, and you get more available CPU because you're waiting less.
Yeah. So it's a huge benefit to any workloads, and I think this is more important than the big flashy millions of IOPS numbers. I mean, that's always the kind of shock and awe that you see, like, oh my gosh, 3 million IOPS, but look at the latency. So I just want to share a few latency points with you. I've got there's tons of FIO numbers that we could look at until our eyes bleed, but I think this is kind of a better way to just summarize it. And the two types of devices that we've done testing on are the Intel P3700, which is a NAND-based SSD, and then the Intel Optane P4800X, which is the fancy new 3D XPoint, super low latency media. And you can really see, what's capable here with Scribe and HyperCore Direct is that you've got, latencies including, and you can look at the P99 and P99.99 latencies are incredibly low. In the case of 3D XPoint, I mean, 62 microseconds, 99.99% of all I/O is faster than 62 microseconds. So obviously, these are very, very responsive drives, and we're able to sort of provide that level of latency into the virtual machine. Again, that's important to remember here. These are latencies actually measured from an application in a virtual machine, right? FIO running virtualized. So, and
So
yeah,
that's
sorry.
with the data protection,
Yeah,
72 microseconds, write, 99.99
yes.
percentile.
Yeah, it's
Wow.
it's impressive, honestly. And that when we were working with Intel with they gave us access to their lab with the Optane drives, and they've been aware that virtualization has a problem with Optane, right? That it's very tough to get reasonable latencies in virtualized environments.
Well, that's what happens
with
when
the
you
fast
tow a
media.
horse trailer behind a Lamborghini.
Yeah. So seeing these latencies and just as a comparison, like bare metal latencies on Optane are probably like the high single-digit microsecond ranges on like reads and writes, like 8 to 10 microseconds. So in a VM, you're talking 20, 26. There's definitely overhead there, but that's a lot faster than than traditionally has been possible. So.
Yeah. And I picked up some of the 32 gig M.2 ones that are intended for desktops and put them in adapters. They work fine in the servers. So a little bit of Optane is 80
Yeah,
bucks.
it'll go a long way. Yeah.
Yeah, it was like $80 for the M.2 cart and $15 for the adapter. It's like, oh look, a little bit of really fast.
That'll help though. I mean,
Well,
if you're
for something like what you guys do, it would be a great place to put the write buffer because you can't do NVRAM in standard hardware.
yeah. Yeah, and using that as sort of that fast tier or putting the journaling on that tier is really what's going to be able to get that right response back to the
Yeah, and
as
32
soon as
gig is
possible.
probably enough.
Yeah. So I apologize for the small numbers here on this chart and everything, but I'll kind of just walk through it and kind of explain. So, the low latency, while being important at one VM, is really important in an environment. You need to be able to scale that up to many VMs. And so here what we're showing is, along the bottom here is just number of VMs from 0 to 64. And in this case, you can see even running 64 VMs, at the different lines indicate different numbers of IOPS per VM. So in this case, the blue line on the bottom, 1,000 IOPS in every VM, 64 VMs. And you can see that nice flat line along the bottom. As you add more workload and do faster I/O rates, 10,000, 15,000 IOPS per VM, at the top line here, you're approaching the limitations of the drives themselves. But I, again, apologize for the squiggly line there. I should have run this test a little bit longer, but that's kind of the idea, is that you see the scalability here in the level of performance as you're adding VMs. And one thing that kind of a geek out point here that's interesting to me, and kind of to summarize the challenges in making NVMe work efficiently in a software stack, and it's a little bit visible here on this blue line, which is the 1,000 IOPS per VM, the lowest I/O rate here. At the very left, you see it really jagged, and the latency actually goes up a little bit at the low end. And this is actually due to some of the hybrid polling that we're doing in Scribe. And at low I/O rates on this version that we were using, it's challenging to use the resources of the machine efficiently when you have low levels of I/O coming in. And this is a pretty interesting problem. There's a great article that came out recently in the Communications of the ACM that summarizes this. It's called "Attack of the Killer Microseconds." And I suggest taking a look at that article, because it's pretty fascinating. And the summary is that there are basically in use today, there are two different mechanisms for waiting on asynchronous events. There's one mechanism which works very well at nanosecond timescales, which is you just spin and wait for the completion of the event. And then there's another mechanism which works really well at millisecond timescales, which has been great for spinning disks and SATA, SAS-based controllers and everything, where you have IOs completing in a millisecond.
Right, well,
that process can go to sleep. You can call into a scheduler and saying, hey, wake me up when this interrupt comes in, or something. And that's an expensive mechanism when you're now in the realm of
interrupts are too slow.
Latencies. Yeah.
Interrupts are the right thing when you can go, I'm going to go over here and do something else.
Yes.
Make a cup of tea.
But when that interrupt comes in, you're talking about context switch. And context switch, as I mentioned earlier, is potentially microsecond-ish expensive. And that gets tricky. And so it is a problem in computing and in operating systems of how to efficiently handle these microsecond timescale latencies. So anyway, that's kind of a geek out point. I recommend reading that article, though. It's pretty interesting. So that's kind of HyperCore Direct in a nutshell. We have this landing site for NVMe now at scalacomputing.com/NVMe. We've got the white paper that we initially published a couple weeks ago there, and I would say keep an eye on this spot for more studies and performance tests as we do them. We'll be placing them there, and further announcements around HyperCore Direct. So.